Hello, everyone, and welcome to another episode of Eyes on Earth. We're a podcast that focuses on our ever-changing planet and on the people here at EROS and across the globe who use remote sensing to monitor and study the health of Earth. I'm your host for this special episode, John Holt. The Landsat program changed the world in 1972 just by looking at it. On a planet now orbited and observed by thousands of satellites, one where Earth's surface imagery is just a tap away on any smartphone, it's really easy to lose sight of just how revolutionary that idea was. By the time the first Landsat was launched 50 years ago, the United States had spent a decade enamored of the concept of space exploration, of landing on the moon, of pushing farther and farther into the galaxy. The notion of turning the eyes on the sky toward our terrestrial home was both novel and controversial. But Landsat would ultimately serve to reshape our understanding of the planet we share. It put space-based land remote sensing on a path to becoming what it is now, a part of our day-to-day lives. So on today's episode of Eyes on Earth, we're looking back at some of the things our guests have shared about the unique value of the unparalleled Landsat data record. We're doing this because Landsat is turning 50. As the anniversary implies, that means 50 years of imagery. Week by week, month by month, year by year, these satellites have built a timeline of change for the entire planet. We can map crop health, wildfire histories, gains or losses in surface water or glaciers, damage from invasive plant species, and so much more across multiple decades. The scientific value of that history is simply staggering. And there are countless examples to show why. Our audio archive is chock full of them. We're only going to scratch the surface today by revisiting conversations with a handful of the thousands of data users who've leaned on the enviable public resource maintained, curated, and shared by the data stewards here at EROS. I'd encourage you to learn more about Landsat by visiting our full podcast archive, which is located at usgs.gov/EROS or available through Apple or Google Podcasts. First up today, we have Bob Schuckman. Bob is the co-director of the Michigan Tech Research Institute, and he had some words to say about the Landsat archive in episode 57. The context here is a research project that had Schuckman and his collaborators using Landsat data to track pollution and invasive species in the Great Lakes over time. Without further ado, here's what Bob told host Jane Lawson about Landsat's history back in August of 2021.
Why is remote sensing so useful for some of those research and monitoring efforts?
The short answer, Jane, is think about the remote sensing satellite time series that we have. It is a time machine. It allows us to go back a couple of decades now and look at some of the water quality changes. A lot of times we don't have the resources or the intuition to go out in a research vessel and measure invasive species 5 years before we really realized there was a problem. So by using the Landsat time series that goes back to the early 1970s, that allows us to fill in measurements vis-a-vis the remote sensing that frankly we didn't have enough sense to measure during the period that the problem was occurring. Time series chlorophyll, for example, benthic cladophora, water clarity, all help us better understand what is the health of the Great Lakes, where have we been, where are we now, where are we going.
Once again, that was Bob Schuckman on episode 57 of Eyes on Earth, titled Landsat and the Great Lakes. Next up, we have Jane again, here talking to Dr. Sarah Hart about another project that leans on Landsat's long archive, the study of invasive bark beetles in Colorado and the damage they do to the forests. This audio comes from episode 64, which is called Colorado Bark Beetles.
So we're talking, like you said, about tiny insects, about the size of cooked rice, right, Dr. Hart? How does a satellite in space, particularly Landsat, offer advantages to studying those tiny insects that you wouldn't have on the ground?
One of the things that makes studying any disturbance hard is that they tend to happen infrequently in time, and things like bark beetle outbreaks can unfold across these broad landscapes. having data from Landsat with its relatively fine spatial grain, as well as kind of this long record, really allows us to figure out how these outbreaks are spreading across landscapes and where they're initiating, that we couldn't get at with just going out and trying to walk around in the woods and look for the outbreak. Oftentimes we don't know the trees are being attacked until they're already dead. And so Landsat really provides us with this great temporal record that's critical to understanding the dynamics.
Because you can see the trees that are dead from a Landsat scene or image.
Correct. Yeah. So as the bark beetles attack the trees, you can imagine what a dead tree looks like. The needles start to turn a red color, and then eventually the needles fall off. And so we can use Landsat to tell where once there was green, healthy trees, and now there are red and dying trees.
The depth of the Landsat archive wouldn't mean much if it weren't for the open data policy. Until the policy took effect in 2008, every Landsat scene had a price tag. Once the price tags disappeared, Landsat science exploded in the United States and all around the world. In 2021, I spoke to Rob Skaken and Ellen Whitman of Natural Resources Canada about their work to remap historical burn perimeters across their country. A lot of those older fire perimeters were incredibly inaccurate. Let's hear what Rob had to say about Landsat's archive and the open data policy to make it possible for them to correct the record of Canada's fire history. That's the title, by the way, of episode 53, so put it in your queue if you'd like. Here's Rob.
It actually goes back a number of years. Actually, it was the early 2000s when the Canadian Forest Service started creating fire perimeters from Landsat. And this was really just to improve the area burn mapping, where the fire management agencies had mapped using sketch mapping and the aerial GPS methods. These map perimeters from Landsat, since we started creating them, they feed each year into Canada's carbon accounting system. And that's used for the annual reporting on emissions from forest wildfires. So again, the reason why we wanted to use Landsat is just having this better data leads into the better estimates of area burned and better inputs to more accurately model carbon emissions. What's interesting is that even today, we still continue to create these perimeters from Landsat because some of the agencies still apply some of these conventional methods. But when we actually started doing this work back in the early 2000s, we actually couldn't remap all the conventional perimeters of the agencies. And that was largely due to cost restraints. And we had to target, say, the largest fires that we could remap because they had the biggest impact on carbon emissions. But once the open data policy came, later on in the 2000s, we were able to retroactively update more of the conventional fire perimeters dating all the way back to 1986. So for our study, this is how we generated our calibration, or this is how we were able to obtain our calibration data, because we had already Landsat fire perimeters that were created for carbon accounting that we're now going to use for our study to create an area-based adjustment model. So from 1986 to 2018, we collected all of our paired samples of Landsat and conventional perimeters, developed an area-based prediction model that we then applied back through time.
Rob's talk of carbon emissions ties into another program for which Landsat is the key data source: monitoring, reporting, and verification of carbon emission reductions. These MRV systems, as they're known, are meant to encourage reductions in deforestation in the developing world. We ran into Andres Especo of the World Bank at the Landsat 9 launch in September of 2021. Here's what he had to say about the importance of the Landsat archive on episode 61, which is called Landsat 9 Launch Part 2.
I work for the Climate Change Group, more specifically for the Climate Funds Management Unit. We are managing around $1.5 billion in finance to countries. We provide some finance in order to set the necessary systems to report to our funds on the emission reductions that they generate from avoided deforestation and forest degradation and enhancement of carbon stocks. And then we have another pot of money where basically we pay for those emission reductions. This program has been there for more than 10 years. And as you can imagine, the payments are conditional to emission reductions, and those emission reductions, they have to be estimated, they have to be measured through MRV systems, measurement, reporting, and verification systems. We provide some countries to set their MRV systems in order to enable them to report us the results. I work with partners at WWF to create the capacities in the countries to implement these MRV systems.
How key is Landsat to those MRVs?
I mean, it's really the cornerstone. You can establish forest inventories, you can conduct terrestrial inventories, but in many of these countries you didn't have anything in the past, right? So you cannot establish a baseline. The only way to do that is with historical imagery, and the only systematic observation of the Earth that we have all the way from the 2000s, 1990s is basically Landsat.
Right. Critical
exactly.
to the job.
Exactly.
Right.
Without Landsat, we won't be able to pay anything.
One especially useful tool in the Landsat toolbox is its ability to measure surface temperatures. That, in turn, makes it particularly useful for cities, which tend to be hotter than the rural areas that surround them, because parking lots, buildings, and pavement trap and retain heat. The city of New York is among those that have used Landsat data to map hotspots. Let's listen to Jane again, here speaking with resiliency planner James Catone of the New York City Council and scientist Christian Brannon. We'll hear James first.
We spent some time looking at the satellite data from Landsat, which it's like an image composed of pixels with a single temperature reading. We were thinking of publishing this heat map on the council website as a public-facing product, and we wanted to make sure that we were putting out something that was as sort of accurate and not misleading as possible. So we wanted to make sure that we were averaging temperatures and not sending like one particular temperature reading from one particular day. I had connected with the New York City panel on climate change for part of my work previously. And so I reached out to them to ask who we should talk to understand how to work with the Landsat temperature data. They connected us with Christian.
Dr. Brannon, how did you lead them to their resulting map then?
It was a great conversation with James and data scientists about how to best use the data. Landsat is capturing data over New York late morning, and so you have to take that into consideration. It's not the hottest time during the day. It's also not at night when you might be curious about how much warmer the city is in comparison to rural areas due to all that energy that's absorbed during the day. However, it does give you a good sense for the relative surface temperature throughout the city at that time, in late morning. What I explained to James and his colleagues is that the hottest areas in the city, the locations that have, relatively speaking, higher surface temperatures, they're going to tend to always have those elevated land surface temperatures. And so the cooler spots, water bodies, vegetation, they're going to tend to be cooler. And the hottest areas will tend to stay warmer. Industrial areas, blacktops, concentrations of concrete and asphalt. Instead of just using the raw land surface temperature value, which is going to fluctuate quite a bit, if it rains on a given day or if it rains the day before, I encourage them to think about which areas tend to be hotter when you look at multiple images and which tend to be cooler. I thought that would be the better approach. That's what I'm often encouraging folks to do when they use Landsat data. And I think that they found some success and were able to create an amazing tool.
Another amazing tool made possible by the Landsat archive is Landfire. That program represents a multi-agency partnership that uses Landsat and other data sources to create incredibly comprehensive geospatial map layers for the United States and insular areas. These map layers tell you what type of vegetation exists on the ground, they model available fuels and disturbances to the landscape, and so much more. Landfire is just one of many land cover datasets produced here at EROS with Landsat, and they're useful for a dizzying array of research projects and applications. We heard about one of them on episode 24 in April of 2020, when Frank Fay of the USDA Forest Service walked me through an online tool called Wildfire Risk to Communities. It's a tool that basically estimates general fire risk for all the homes and buildings in the United States. Here's Frank talking about how the tool was made.
Yeah, Landfire is a program that maps vegetation and fuels. It is almost 20 years old now from the first time somebody thought that this was possible. Landfire uses a combination of satellite imagery from Landsat, field plots, and biospatial information like gradients, like elevation and aspect and rainfall and growing days. We used a model called the Large Fire Simulator that was developed by the Fire Lab in Missoula, Montana. That model combines topography, which is a USGS product, fuels from the Landfire project, weather from the National Weather Service, and then fire history. Those four things are combined to create a simulation based on probabilities of a single fire year. Then that fire year is repeated over and over, tens of thousands of times. The resulting product is a map that shows the likelihood that a fire will occur and the intensity.
So Landfire was a very important part of the mix of data sources for this product. Was it always part of the discussion?
Landfire is really the only option. There are no other data sets that have the scope, scale, and detail needed to run this simulation. I don't think we talked about any options for vegetation and fuels besides Landfire because we already knew that the Landfire data would work.
Let's close out by revisiting a conversation from episode 2, where Steve Young spoke with former EROS Science Branch Chief John Dwyer about an incident that truly brought the value of Landsat into focus worldwide, the 1986 Chernobyl nuclear disaster in Ukraine. John, who passed away in 2021, talked to Steve back in 2019 about how that event changed the way the world looked at Landsat. Now, at this point in the conversation, John had already explained that Landsat 5 captured an image of the Chernobyl area shortly after the meltdown. We'll let Steve take it from here.
We determined that we have this image, and it's here at EROS. Did that 15 minutes of fame come to roost here in EROS? Did people start hearing about this place and wonder what's going on?
It did, and obviously inquiries were coming in, probably from other federal agencies as well as the news media in terms of, okay, we hear you guys operate these things called Landsat. Do you guys have imagery? What can you see? And that kind of stuff. Our center director at the time, Al Watkins, was really handling all of that, communication with the other agencies and the media. But it did result in a CBS News truck coming out one night for a live interview and feed. And, they interviewed Al. They brought their camera crew into the data analysis lab. I showed the images on the monitors, they filmed that, and that was our claim to fame. And it probably was an incident that really did bring satellite remote sensing a little bit more into the public front. I mean, it had never been hidden, but it wasn't something the average person was aware of. I mean, today, imagery from Google Earth, whether it be satellite, aircraft, whatever, is ubiquitous, right? But, keep in mind, 1986, personal computers were just coming online.
So it sounds like this is a fairly significant validation of an important event in global history, this image we had. Does the EROS archive include other significant images through time? And if so, can you give us some examples?
Well, I'm sure it does. The first Gulf War is an example when Iraqis were burning the Kuwaiti oil fields. I mean, we captured that big time, stark imagery that you could see not only the smoke from the flames, but over time the residue that lands on the soil, from the hydrocarbons. So there's a number of things like that. The value of the Landsat archive is that the effort to continuously, comprehensively image the Earth's land masses enables us to look at changes over time. Looking at imagery over the Aral Sea, for example, we can see how drawdown of the lake due to water consumption exposes soils, and in that area, a lot of those salts and things have some health issues associated with them. Wildfires, that's become a ubiquitous tool for mapping wildfires every year. The extent of damage from flooding, hurricanes, tsunamis, a lot of that. Landsat is always called on to look at response to natural and human disasters. And that's what the Landsat satellites were designed to do. Basically a global monitoring tool.
And that's it for this episode of Eyes on Earth. Thank you so much for joining us to revisit some of our favorite moments on Landsat's history. As you know, all our shows are available on the USGS EROS website. You can also find a wealth of information, podcasts, documentaries, stories, interactive tools, even educational curriculum at a new site we've launched to celebrate Landsat's 50th anniversary milestone. It's called Landsat Legacy, and you can find it at usgs.gov/Landsat-Legacy. Take a look. You won't be disappointed.
This podcast
is a product of the U.S. Geological Survey, Department of Interior.